In this video, we'll cover Boolean algebra and logical tests. By the end of this video, you should understand what a logical test is and how you might use them in data science. You'll know what the important logical tests are and what the important logical operators are. The R code that I show in this video is available on Elms, and you may want to take a minute to download it and open it if you'd like to follow along on your own. So what are logical tests? Remember that computers store and process data using 0-1 binary values. Many operations on computers can be thought of as evaluating a logical test. And a logical test is a statement that evaluates to either true or false. For example, 5 is greater than 3 is true, 3 is greater than 5 is false. So how are we going to use logical tests in data science? Often, we only want to look at a subset of data. So for example, filtering a list of products to 4-star or better ratings. How would you describe that as a logical test? You might say, I'd like to keep products if the rating is greater than or equal to 4 stars. This is exactly what I mean by a logical test. R has a full set of logical tests built in. They compare two values or expressions. In R, a logical test will always return a value of either true, false, or NA. You'll notice these are in all capitals. Logical values are always all capitals in R. A true means the logical statement is true. A false means the logical statement is false. We'll talk about why you might run into NAs when we get to this section on missing data. You should be familiar with some of this from mathematics or philosophy courses. So what are the logical tests that are available in R? I'd like you to think of the expressions A and B. These could be almost anything that you can store in a variable, but I think it's most convenient to start out with just to think of them as numbers. So the logical test greater than is A followed by a greater than sign, followed by B, and it returns true if A is greater than B and false otherwise. Likewise, there's the less than test. A followed by a less than sign, then B returns true if A is smaller than B. The greater than or equal and less than or equal to tests are the corresponding sign followed by an equal sign. Greater than or equal is true if A is greater than or equal to B. There's also the equality test. This is denoted by two equal signs next to each other. That keeps it distinct from the assignment operator, which remember can be just one equal sign. The equal logical test returns true only if A and B are exactly equal to each other. There's also the not equal test, which is an exclamation point followed by an equal sign. This returns true if A is in any way not equal to B. Let's take a look at this in R. Remember that every logical test is going to return a logical result that is true, false, or NA. So at the very simplest level, we have greater than and less than. So you could think of asking R, is 5 greater than 3? 5 is larger than 3. So the result is true. I could also ask, is 3 greater than 5? 3 is smaller. So as we expect, I get a false. These are some pretty simplistic tests. I would expect anyone in this class to be able to tell me if one number is bigger than another number. So usually what's going to happen is you'll have operations on one side or another. So for example, I could think of asking R, is 10 less than 20 minus 9? So if you were to evaluate this by hand, 20 minus 9 is 11. 11 is larger than 10. 10 is smaller, therefore I should get a true. What if I were to ask R, is 10 less than 20 minus 10? So in this case, 20 minus 10 is 10, which is equal to the left-hand side. This is a less than sign, so that means I get a false. R also has greater than or equal to and less than or equal to, so we can work through a couple examples. Thinking, is 15 less than or equal to 5 times 3? Again, 5 times 3 is 15. Those two are equal, so I should get a true. Is 15 less than or equal to 5 times 2? 5 times 2 is 10, so there I get a false. I can do the exact same thing with greater than or equal to. 10 is greater than or equal to 100 divided by 10. 100 divided by 10 is 10, so I get a true. If I have 100 divided by 20, that is 5. 10 is also greater than or equal to that. Likewise, I get a true. You can also test for equality. We'll make this a little bit more complicated. I'll define two variables. I'll define A to be 5 times 4, and I'll define B to be 10 times 2. If we take a look in the Environment Explorer, you can see that both A and B are valued as 20, as we'd expect them to be. So now let's take a look at what would happen if we tested whether or not A is equal to B. Remember, the test for equality are two equal signs to distinguish it from the assignment operator. A and B are both 20, and what you can see there is that when I test for equality, I get a true. Now I could test to see whether or not A is equal to 20.1. We know it's not. Running that bit of R code, you can see that I get a false. There's also the inequality operator, which is an exclamation point followed by the equal sign. I could test whether or not A is not equal to B. Since we know they're equal, I get the expected answer of a false. I could then test whether or not A is not equal to 20.1. and you see that I get a true. The logical tests form the first part of Boolean algebra. They allow us to evaluate expressions and determine how they relate to each other, whether they are equal, greater than, less than, or so on, returning either true or false statements. The real power of Boolean algebra, though, is that you can combine these logical tests together. So by way of an example, think again about searching for products. Suppose you wanted to limit the list of products you were searching for to those with 4-star or better ratings, but they also cost less than $20. How would you describe that as a logical test? You might say, I'd like to keep items if the rating is greater than or equal to 4 stars and the price is less than $20. How might you implement this in R? You can chain together logical expressions in R using logical operators. R has the full set of logical operators built in. They combine with logical tests to form what is called Boolean algebra. This is a field of mathematics built around true and false values. R's logical tests and operators allow you to form any possible logical statement. So what logical operators are built into R? Again, let's think about expressions A and B. These can be almost anything, but it's super convenient to think of them as numbers. The first logical operator is the AND operator. So you put AND in between A and B, and the result will return true if both A and B are true. The OR operator, so A followed by the vertical line, and then B, returns true if either A or B are true. So it's only false if both A and B are false. Next is the XOR operator, spelled XOR. What this is actually a shortcut for is the exclusive OR operator. It's a function that takes A and B as arguments. The XOR operator returns true if either A or B, but not both are true. Lastly, there's the NOT operator. This only takes one argument, so it's an exclamation point followed by an expression. In this case, not A will return true if A is false. If you ever try and feed something that is not a logical value, a true-false value, to one of these logical operators, R will coerce it to a true-false value before evaluating. If you recall from several videos ago, there's an order of operations in R. This order of operations applies with Boolean algebra as well. So you might want to think of how would R evaluate this following expression, where I have 5 plus 3 is greater than 6. R will always evaluate arithmetic first, followed by logical tests, and then logical operators. So in this example, 5 plus 3 will be evaluated first. That gives a result of 8. Then 8 will be compared to 6 with the greater than operator. 8 is larger, so the result would be true. Remember that logical operators, things like AND and OR, are evaluated even later in the process. So in this case, we have kind of a complicated logical expression, 5 plus 3 greater than 6, and 8 plus 2 less than 9. The way R evaluates this is first to evaluate the arithmetic, so adding 5 plus 3 and 8 plus 2. That gives us 8 is greater than 6, and 10 is less than 9. R then evaluates the logical tests, the greater than and less than signs. 8 is greater than 6. That gives us a true. 10 is not less than 9, so the result there is a false. That leaves us with true and false. Remember, the AND operator only returns true if both sides are true. That's not the case here, so the result is false. I've given you this statement here, and just like every other expression in R, the statement is unambiguous. R knows exactly how to process this statement because it has a well-defined order of operations. The fact is, looking at this statement, it's still pretty confusing to read. This can impact the transparency of your computer code. I recommend that when you have complicated logical expressions like this, that you can make them clearer by adding extraneous parentheses. So in this example, I put each logical test inside parentheses, so it's very clear to anyone who's looking at it exactly how it should be evaluated. Now the result here will be exactly the same, whether you include the parentheses or not. It just makes it easier for someone to read. So again, let's take a look at this in R. Remember that logical operators can combine logical tests, chain them together in a bunch of different ways. So the first logical operator that we went over is the AND operator. Remember, the AND operator looks at both sides, and it returns true if both sides are true. So in the very simplest case, I could look at the AND of true and true. Both sides are true, so I get a true. But if I took the AND of true and false, one side is true, but the other is false, so I should get a false. Now again, these are pretty simple examples. When you're using logical operators, you're combining logical tests, so you'll probably do this in a little bit more complex fashion. So let's start out by defining 3 variables. I'll call them big, which is 100, medium, which is 20, and small, which is 1. So what I can think of doing is testing whether or not big is greater than medium and small is less than medium. Remember, big is greater than medium, so that left-hand side is true. small is less than medium, so that right-hand side is true. Evaluated with the and operator, I get a true. I can think of a different case where I look at is big larger than medium and is small larger than medium as well. We know small is smaller than medium, so evaluating that, the left-hand side is true, the right-hand side is false. With that and operator, we get a false. I want to be really clear here. The stuff that I've put in the console, I've used parentheses to make it easy to read. The order of operations tells us that the logical operators are evaluated after the logical tests. So I actually could have typed in something that looks like this for the last operation. It evaluates the exact same way. It's just a little bit more difficult to read because your eyes don't gravitate towards the parentheses first. There's also the OR operator. Remember, OR returns true if either the left-hand side or the right-hand side are true. Just to refresh your memory, when I used the AND operator on that last operation, we got a false where I looked at whether or not big is greater than medium and small is greater than medium. If I replace that with an OR, again, the left-hand side is true, the right-hand side is false, but the OR operator only requires one of them to be true, so I get a true. Go ahead and clear my output window here. There's also the XOR operator, spelled XOR. XOR returns true if either A or B are true, but not both. This will probably come up less often in your data analysis, but suppose we use the XOR operator on that last logical test, looking at whether or not big is greater than medium, XOR small is greater than medium. Remember, the first logical test was true, the second was false. That means one is true, but not both of them, so we should get a true. Let's look at a case where both of the logical tests are true. In that case, XOR returns false. Lastly, we have the NOT operator. So again, what the NOT operator does is it returns true if whatever it's sitting before is false. So let's just think of a simple case, small greater than medium. Remember, small is smaller than medium, so that result is false. But if I put the NOT operator in front of it, then I get a true. So far, we've thought of performing logical tests on only numeric data. The fact is, you can apply logical tests to any kind of data. So for example, I could test whether or not the text reproducibility is equal to the text reproducibility. These are exactly the same, and so the result that I should get from this logical test is true. This is exactly the way that it works in R, and logical tests can be applied to any kind of data that you have in R. Likewise, you could test whether reproducibility is equal to transparency, and in this case, these two pieces of text are not identical to each other, and R will return false. In general, the equality logical test is going to make a lot of sense with non-numeric data. Two things are going to be equal. The result will be true if they are identical. R has very specific rules about what is identical, and essentially for two things to be identical, they must be exactly the same. In the case of text, this might be a little tricky at first, but for text to be exactly the same, every letter, every character has to be exactly the same, and it means the same capitalization, and the spaces must be the same. So for example, if I were to take reproducibility and test whether or not it's equal to all capitals reproducibility, R will give me a false because every letter, capitalization, and space isn't exactly the same. These two pieces of text aren't identical. Likewise, if I take the word reproducibility and just put a space after it, it's not equal to the original reproducibility text. Again, because there's that extra space there, R says these are not the exact same pieces of text, therefore they're not equal to each other, and the result is false. So what about the other logical tests? Can we use those on non-numeric data? Sometimes you can, other times R will give you an error. When you can use them, the rules of Boolean algebra all still apply. That means that greater than, less than, and equal to are all mutually exclusive. In other words, if A is greater than B, then A can't also be less than B or equal to B. Boolean algebra also requires that those tests are exhaustive, which means that between A greater than B, A less than B, and A equal to B, one of those must be true. Those operators also have to be transitive, which means that if A is greater than B and B is greater than C, then A must be greater than C. There are other rules to Boolean algebra as well. They're really straightforward to think about with real numbers, but a lot harder to think about when you deal with other types of data. Importantly, these logical tests, greater than, less than, greater than or equal to, and so on, all work with R text. These tests are unambiguous. R is always going to evaluate a given logical test on two pieces of text data the exact same way. This is not as straightforward as numbers, so there's a lot of rules that R has to follow. For example, is cat greater than or less than dog? But is cat with a capital C greater than or less than cat with a lowercase c? They're certainly not equal to each other. So these rules don't always make intuitive sense. My advice is you should generally avoid making logical tests on text unless you know exactly how R is going to evaluate the test. Let's take a look at this in R. So again, logical tests can work with non-numeric data. The most common case is when you're testing for equality, and that works mostly like you think it should. So if I test whether or not the string cat is equal to that exact same string cat, I get a true. But if I test whether or not cat is equal to dog, clearly those two things aren't equal, so I get a false. The tricky part is that when you're testing for equality with text, the text must be exactly equal. The capitalization, the spaces, everything must be exactly the same. So if I test whether or not cat with a capital C is equal to cat in all uppercase, I get a false. Likewise, if I test whether or not cat is equal to the exact same piece of text but with a space in front of it, because there's that extra space there, I also get a false. Other logical tests also work with text data, but the rules are sometimes really hard to understand. So for example, I could look at whether or not dog with a capital D is greater than or less than dog with a lowercase d. It turns out that's true. But then if I modify that just slightly and look at whether or not dog with a capital D is greater than or less than dogs with a lowercase d, I get a false. So just adding that s onto the end changes the result from true to false. There's very precise rules behind this in R, but the fact is sometimes they're really hard to understand. These logical tests can also work on objects. Equality requires the objects be identical. That's relatively straightforward. Other tests, like greater than or less than, may or may not give a result. Often, you'll get some kind of error exception when you try and do an inequality test on two objects. For example, if you try and run a greater than or less than test on complex numbers, it doesn't work, and you get an error exception. Generally, even if these things do work, they may not make a lot of sense.